Okay, good afternoon. This is the last of the 663 revision videos, and we're just going to talk about overhead lines, just a few things you need to make a note of. Also, if you've watched all the other videos, there's enough information in those to support that as well. Just one point on, say, current or voltage transformers. TX means transformer. You remember that if we have a transformer like this, say 11 kV coming in, and say 230 volts here, single phase, I'm just showing single phase. Then if we want to measure the current flowing through that line, we effectively have a current transformer on the line, and the secondary of that transformer is taken off, and that measures current. Usually it's done electronically and digitally converted to send off to your control room. But the important thing is, and you may get questions on this, is that this secondary on this current transformer has to be connected to earth on one side. The reason for that is because if there's a lightning strike or there's another fault on the line which produces arcing, then the voltage on this line could rise rapidly, and it could cause a flashover to the secondary inside this current transformer. So for safety reasons, to protect the equipment and to protect personnel who might be using this equipment, this side must be earthed. Okay, remember that one. On overhead lines with wooden poles, so there's an overhead line, there's a series of poles running in a straight line. At the top of the poles there's a load of metalwork that's supporting the lines, which you can see as you observe these poles. And the electricity safety and quality regs say that if these are wooden poles, and if they are greater than 3 meters off the floor, they're classed as out of what we say is out of reach. So because they're out of reach, they do not need to have an earth bonding conductor down to the ground for every single one. It's at the discretion of the distribution network. Usually you tend to bond only the ones where there's a transformer or other switchgear hanging off the pole. Okay. I put quite a good video up about by somebody else who did one on corona discharge. And when you have an overhead line, the electric field produced by the current going backwards and forwards in that conductor can cause ionization of the air particles, and what that causes is a sort of visible glow and a hissing and buzzing sound. But because it's all along the line, it can also increase your power losses in the line. So a way of reducing this effect is to split this single conductor into, say, 2 or 4 single conductors, and so because the current is divided by 4 into each conductor, the field is reduced. So the overall effect of the field is reduced. And if you use a spacer to keep these apart, then the effect works quite well, because the current is effectively divided into 4, so you've got 4 smaller fields, so the overall effect is less. So that's why you have these spacers. Okay. Another problem on overhead lines, there's our transformer, 11 kV. Here is our overhead line going off there. And it's effectively Earth, isn't it? If there's a lightning strike on the line, this rapid instantaneous rise in voltage can produce can induce a high voltage in the line. And if you happen to be working at or near this transformer or the switchgear associated with it in, say, a substation, then you could get an electric shock if you were working on that, if the voltage is very high. So you have to be very careful when working on lines if there is a thunderstorm brewing in the background. Okay. On sag, you know that the basic formula for sag equals WL squared over 8S. And if I transpose that, I get T8S equals WL squared. So sag equals WL squared over 8T. So you can see here that as the tension goes up, the sag would go down. So the less tension there is in the cable, the greater the sag. Okay, so it's what we call sag is inversely proportional to the tension. Okay. So you do occasionally get questions on that as well. Okie dokie. Thanks very much. Cheers now.